because symmetrical things tend to be biological, and attending to symmetrical things tends to have advantages for reproductive survival, human beings and certainly other animals find a certain beauty to symmetry, or at least they feel a reward for noticing, attending to symmetry. Now, this right over here is a circle, and it's highly symmetrical. It's a nice two-dimensional object here. You see, if I rotate it like this, other than the reflection, you don't see any change. And I can rotate it on any axis I want, and it will remain the same. High symmetry. On the other hand, a square is less symmetrical because you have to rotate it by 90 degrees before it becomes the same. So that's an example of symmetry. You do something, and things remain the same. Now, a lot of the laws in science are symmetrical, conceptually and mathematically. And when something doesn't change, we call that a symmetry in science as we do in geometry and in mathematics. So, for example, if we go out into space in different directions and the laws of the universe are the same, we say they are symmetrical with respect to space. And if we believe that the laws of the universe, as most but not all people do not change, with time, we believe that they are going to be time invariant or symmetrical with respect to time. In fact, the law of conservation of energy is directly related to the idea that the laws of the universe cannot change with time. And symmetry has a real beauty, and scientists look for symmetry in mathematical theories. One, because we're attracted to that naturally, but two, because the universe has dished up so many symmetrical thingies. Now, one of those areas that's causing problems is quantum mechanics. Another area is the Big Bang. And another area, especially more and more these days, is time, which folks are saying, hey, I don't even know if that's a fundamental concept. It might be derivative of other things, manufactured on top of other things in the universe. And a lot of this comes from the fact that scientists have spent a long time trying to reconcile two concepts, specifically quantum mechanics and general relativity, without success. And they're looking for answers because the fact that these two theories exist, and one essentially at the large scale and one essentially at the small scale, works well, but they're incompatible, is an asymmetry. Scientists are looking for symmetries. For example, one area where symmetry has worked quite well is in unifying 3 of the 4 forces of nature. And what happens is that at higher and higher temperatures, the different forces come together. They become the same. The same equation describes all of them. So far, we haven't been able to put gravity in the mix, but everybody's sure that it is going to fit in there some way, somehow, if we can just figure out how. Because we believe in symmetry. The universe dishes it up. But there's other aspects of symmetry that are a problem. Like, for instance, whenever you have something that just is, for no damn reason, that's asymmetrical. Something ad hoc. And one of the biggest problems is this idea of the fundamental constants of the universe. There's a bunch of them. One of them is the speed of light. Why is it the number it is and not something else? Scientists have believed for a long time we should be able to come up with a reason. And the thing is, we haven't been able to. And one of the things that is occurring is the belief that chaotic fluctuations occur to create multiple universes. Multiple universes. Universes beget universes due to the fluctuations of things called scalar fields, which is essentially related to energy, the quantity of energy in space, which fluctuate pretty wildly, But if you're at a certain level, a very low level, they're not going to explode into another universe. But if you're at a false vacuum, a false bottom, then they can. But it's really rare that they do. It's like the lottery. There's a really small chance that you could win the lottery, but there's a very large chance that somebody will. Maybe not next week, but the week after. And we believe these universes just pop up. And here's the thing about these universes. We actually believe that each of these universes has its fundamental constant set right after, shortly after they're created. And they're going to be all different. Now, the thing that makes this symmetrical is that all these different possibilities occur. Not one, like the one in our universe, but everything possible. That's parsimonious. That's symmetrical, at least to me, and to many others. And the same thing occurred when Hugh Everett came up with his many-world hypothesis explanation for quantum mechanics. Now, Niels Bohr, he was the man, and he just didn't like the idea of anybody interfering with his interpretation. But it was a beautifully symmetric one, and the only one that explained quantum mechanics without this ad hoc notion. Whatever it did, he said, whenever there's a quantum event, whatever that is, it doesn't just happen in our universe. It happens in all universes. But you have different outcomes. So, quantum events are acausal. They are not determined by anything. And this is no longer speculation. This has been accepted. Only crackpots don't believe that. Okay? So what happens is that now we have symmetry. We're saying, oh, okay, now we have a reason. Not the kind of reason you might like, but we have symmetry. That is, if everything occurs, then you can explain any individual result. But listen, they're doing this not just for the Hugh Everett thing, man, that's old stuff. I mean, I'm not sure if that was like 1958 or when. I think that's when that first came out. But now they're talking about time. Why is time only going in one direction? Now, if you think about time, you say, I know, I've heard these stories at the microscopic level, time can go forward or backward and you can't tell the difference. And then folks say, well, yeah, but the universe tends toward disorder. Disorder is called entropy, and so the direction of entropy increase is time, or related to time, or something. But the problem is that equilibrium is the state of maximum entropy. And there are huge areas of the universe which are in equilibrium, including plenty of places on Earth, and time still occurs. It flows forward. And there's no explanation for that. So what they're suggesting is that when universes are formed, they not only form their own physical properties, their constants, they also choose a direction in time. Now, so far, I've only read about two directions, moving toward A and moving toward Z. If you're in any particular universe, what happens is you experience time going forward. But all these different universes, some of them move toward A, and others move toward Z. And in any particular universe, you can't tell the difference, but when you look at the whole multiverse, it's symmetric. You have the same number of universes going one way as the other way. And now, a latest discovery has to do with matter and antimatter. It's always been thought that probably the amount of matter and antimatter produced in events are going to be the same. But just recently, we found when we smash protons together, we get a little bit more matter than antimatter. But the numbers are significant. It looks like it's for real. There had been evidence of this a few years ago, but the numbers were not that clear. This looks like the real thing. And you know, we're explaining this all away the same way. We're saying, well, there's some universes that favor more matter and others more antimatter. Now, you could think, hey, this is just a great way to explain everything, but you can't prove it. Well, you know what? That's what you start with. You start with theories. And even if you can't directly observe things, eventually there may come a way to prove these. And people have actually suggested ways for some of the things I've mentioned. It's terribly cool. Now, my own personal preference is I love this crazy universe we're in. And I want to live in a Baroque universe that has all these permutations. I want to have parallel universes and multiple universes, because I tell you what, when I go in the supermarket and I look at the checkout lanes and I see all these celebrities and stuff, I say, I don't give a flying fuck. But my universe, I care about her.